Hello and welcome. This is Karsten, and today I will give you a little bit information on Ipv6. Now, the content that we see here is an excerpt from the larger Men&Mice Ipv6 training. And this part is about the current status of Ipv6 and why we don't see Ipv6 everywhere. And we have an introduction in Ipv6 addressing, meaning the different IP address types and how they are composed and where they are used. So just let's dive right into it. So what is the current status of Ipv6? This is the current graph showing at the Google Ipv6 status site, and that is the accumulated use of Ipv6 worldwide as it is seen by Google from the search engine. And there we see that worldwide we have about shy of 35% of the world's internet population is using Ipv6. Here we also see in red 624 and Teredo, which were once quite popular transition technologies, that they are not used anymore. The percentage is there 0.00, which means that everything Ipv6 we see is real native Ipv6. It's not tunnels or some transition technology running over Ipv4 anymore, but it's just plain native Ipv6. This is a different picture. Ipv6 is seen by Cisco in their statistics page. And there we see that the countries that have the most deployment of Ipv6 nowadays have more than 50%. So there we see more than 50% or more than the half of all internet traffic in that country is over Ipv6, and Ipv4 is the minority. These countries are India, which is a quite large country with a lot of internet users there. And in India, it's mostly the mobile phone operators. They switched to Ipv6 in the recent years because of the shortage of Ipv4. It's also Greece, in Europe, and Germany. Here in Germany, we have currently around 53% of Ipv6 deployment or usage. And here we see a different picture. This one is by Akamai. And this is the Ipv6 usage as seen by Akamai in their content delivery networks. And I've selected here the United States of America. And we see that the US, which is the big market and a lot of internet users are there, that they are approaching 50%. And they will probably tip over the 50% mark in this year. So it looks pretty good for Ipv6. A little bit about Ipv6 projects and my experience with Ipv6 projects and why don't we see Ipv6 everywhere right now. So there I see three phases with Ipv6, and the first phase is denial and procrastination. So people say, this Ipv6, it's not so important, we can wait, we do it next year. And it's then always we do it next year because it's there's always something which is more pressing, which is more important. And they try to prolong that phase one as long as possible, because Ipv6, of course, is change, and change is always difficult to do. And then there comes outside pressure, and that could be the depletion of Ipv4, but it could be also other outside pressures. Like if your customers are all on Ipv6 and you only have Ipv4 as a company, that can be bad for you. And during the recent COVID lockdowns, I had a number of customers that found that out because they had to send their people to their home offices, working from home. And at home, here in Germany, most people have Ipv6 natively. But then the companies only had Ipv4. So while it is possible to bridge from IPv6 to IPv4 with some transition technologies, it doesn't really work well with video conferencing software, because video conferencing software is mostly UDP driven, and that doesn't really work well when translating in between. It raises the latency, and also sometimes the connection drops. So there were all of a sudden a huge pressure to implement IPv6, and that was not only the enterprises, that was also government, that was schools, and all the people who had now to talk to people that are on IPv6 in their home networks. Even in that phase, when there's outside pressure, I sometimes see open or hidden opposition. So people saying, "Oh, we can't do that because of," or "No, we don't need IPv6," or "We only need IPv6 in the data center, but we don't need that in the office," something like that. But eventually, IPv6 gets deployed, and people work with IPv6. Both the users work with IPv6 and the administrators work with IPv6. The users usually don't care, because as a user, you don't see any change. It just works. IPv6 just works the same way as IPv4. And if you are a user on the internet, there's really no difference at all. You don't recognize if you serve or use your app over IPv6 compared to IPv4. It is a difference for the system administrators, because they have to learn new stuff. But once they have learned, and once they have worked with IPv6 for a certain amount of time, which is usually 1 year or 1.5 years, then something happened, what I call its enlightenment. All of a sudden, people realize that this IPv6 is so much nicer than IPv4. And when that happens, everyone wants to get rid of IPv4. Because it's legacy, it feels old, it's not so flexible as IPv6. You can't do the nice thing that you are used to doing in IPv6. So these are the phases that I see. IPv6 is as much a human challenge as a technical challenge. So people are opposed to change, and if IPv6 enters a network, many things will change in the network. Of course, it's a new protocol. One other observation that I found is that IPv6 cannot be a side project. It cannot be done in like the free time of one administrator. It must have management attention, and it must be 100% backed up by the management. It doesn't work if the upper management wants some exceptions from IPv6, like, yeah, everyone else can do IPv6, but don't do it in my office, something like that. No, that doesn't work. It must be in 100%. Also, you need to know, when you introduce IPv6 in your network, there will be friction, and there will be errors, and there will be breakage. That's normal. You have to deal, and you have to plan for that. Administrators and developers must have a safe environment to be able to innovate with IPv6. So they need to have an environment to test things out, to plan new stuff. IPv6 is so much more flexible and offers different ways to implement stuff that has been done in a certain way in IPv4, that if you really want to have the benefit for IPv6, you have to be able to play with it a little bit before implementing that. So what are actually the benefits of IPv6? IPv6 is much more flexible. So when you have IPv6 in your network, it makes certain configurations much easier. You don't have to have a network address translation. You can, if you like to, so nobody is taking away network address translation from you, but you don't have to. IPv6 has so many IP addresses, there's no shortage. Also, it makes network management and network planning much leaner, easier. It is more flexible by offering less choice. That sounds like a contradiction, but it is true. For example, in IPv6, you only have for a subnet, you have one size, which is the /64. An IPv6 network is always a /64 if there are n machines in there. In IPv4, you have to think of, oh, do I do a 24 network or a 22 or even a /20 network or /16, which is too small. The other one might be too large. You don't have to think about that in IPv6. It's always /64, and /64 is 4 billion times the size of the current IPv4 internet. So that's always enough addresses. And of course, if you have to work with public IP addresses, there's less cost per IP address. One single IPv4 address currently costs around $20 while you get IPv6 for free. There are certain trends to be seen in networks that already deploy IPv6. For example, on the wireless, people start deploying one subnet per machine, per host on a wireless network. With that, you have a natural user separation, even on cheap access points. For example, if you have a guest wireless network, you don't want to have the different users to be able to access the other users' machines. That shouldn't work. And you can buy more expensive wireless access points that separate all the users in the wireless LAN. But for example, some providers would like to open up the wireless access points at home so that people on the street can also use them, roam on the wireless. But these access points, they are cheap access points. They don't do the separation. If you deploy one full subnet per machine on the wireless network, there is a natural user separation. So because it's a different network, you cannot reach the other users on the same wireless because there's no routing between the networks. In the data center, on the other hand, there is the trend to use one IPv6 address per service endpoint. That means if you have a server that has many services, like a server that has a mail service, has a web service, and have a video conferencing service, nowadays, the server has an IPv4 address, and then all different services, they have port numbers. So the web is on port 80 and port 443, the mail is on port 25 and 587, and the video conferencing might be on port 5000. With IPv6, we have so many IPv6 addresses to spare, we can use a single IPv6 address for every service. So the web service gets an IPv6 address, the mail service gets an IPv6 address, and the video conferencing service gets an IPv6 address. There will still be port numbers, but the port numbers are not the only thing that separates the services on the same machine. And there will usually also separate IPv6 addresses for administration and monitoring. This allows for IPv6 overlay networks with security boundaries. So the security in your network is not based on the location and the network topology anymore, but instead, no matter where the machines are located, you put them in an overlay network over IPv6, and they are in that overlay network with the separate security configuration. So that makes IPv6 security much easier. For example, firewall rules, routing configurations. Okay, these were the benefits. Let's have a short look on IPv6. The work on IPv6 started in the IP Next Generation Working Group in 1993. And anyone old enough might remember that that is the time when Star Trek Next Generation was on TV. And that's the reason why it was called IP Next Generation. Then RC 1752 was the first version of IPv6 just a year later. And then the final IETF draft standard was published in 1998. Over the time, IPv6 was then expanded, like with 6.4, which is was a transition technology from IPv4 to IPv6, or DHCPv6. So in this year, we see less and less IPv4 blocks that are available at the regional internet registries, which are the organizations that give out new IPv4 addresses. So ERIN, the North American regional registry, they already run out of IPv4 addresses in 2015. Both RIPE for the European region and LACNIC for South America, they run out of IPv4 addresses in 2020. And both APNIC, which is Asia Pacific, and AFRINIC for Africa, they are on their last /8 block. They will probably run out either this year or next year. And then there is no new IPv4 addresses anymore. And here we see the projection and the real usage or depletion of IPv4 addresses. And there we see that both AFRINIC and APNIC, which is the green and the light blue one, they still have some addresses available, but not much. Also, if a device or a software claims to be internet compatible, it nowadays must support IPv6. There's an RFC 6540, which has been published in April 2012, that mandates that IPv6 support is required for all IP-capable nodes, which actually means that if you go in a shop and you buy a device, and that device on the outside says it works with the internet, and it doesn't explicitly say that it is IPv4 only, it has to support IPv6, else you can bring it back to the vendor and say, oh, this is not right. If it is an internet device, it has to be IPv6 as well. So I won't go into all the details here. The RFC just explains that implementers that update existing hardware or software have to enable IPv6 wherever that is technically feasible. And in most devices that do internet, it should be just a no-brainer to support IPv6 nowadays. It was really a big push that both Google and Apple decided that they check for IPv6 capabilities in the apps that are being uploaded in the app stores for the mobile operating systems, because that really brought the outside pressure for the developers to implement IPv6 and test their applications on IPv6. So now let's see how IPv6 works in a nutshell. So what we see here is what's called the TCP/IP hourglass. And on the bottom of that hourglass, we have the different network technologies like Ethernet, wireless, token ring, and so on. And then on top of that, we have the IPv4 protocol, which is the shim that routes and takes the IP packages from one end of the network to the other end of the network, from one device to another device. And then on top of that, we have the transport protocols such as TCP and UDP or HTTP. And again, on top of that, we have the application protocols, something like web, HTTP, mail, SMTP, or voice over IP with SIP. And if we look at the hourglass with IPv6, it looks very much the same. Just the small part in the middle has been exchanged. So we still use the same physical layer. We still use Ethernet and token ring, or maybe not token ring anymore, or normal wireless and other hardware access to the network. Then on top of that, we run IPv6. That has changed. But then on top of IPv6, we still have the same TCP and the same UDP and the same SCTP that we had before, and also the application protocols, SMTP and HTTP and SIP. They haven't changed. They are just the same. And if we want to run both IPv4 and IPv6 in a network, we can do that. That's called a dual stack implementation. And here we see the IPv4 packet header. And I won't go into details here, but I want to point out that we have a lot of fields in there, and we will see the IPv6 equivalent in a moment. And we will see that the packet is really optimized for 32-bit access. And that's a little bit of a problem nowadays, because most operating systems and most computers nowadays are 64-bit machines. We even have the first 128-bit machines around. And on these machines, access to memory locations for just 32-bit is a little bit more costly than accessing a 64-bit at a time. IPv6, on the other hand, is directly optimized for 64-bit accesses. So everything is aligned for 64-bit. And you also see it's much less cluttered. It's less fields in the package there. A lot of stuff has been removed from the IPv4 when it was taken over to IPv6. A lot of functionality that was built in the IPv4 header has been removed because it has been seldom be used. And in IPv6, that's been implemented as so-called extension headers. And they are only available if they're really needed. So IPv6 is usually faster than IPv4 on the same machine, which is especially true for embedded machines. So if you have some home automation stuff that makes sure that the ambient light in your room is good and the heating is on, all these devices work much better on IPv6 than they do on IPv4. Also, the energy consumption with IPv6 is less than with IPv4 because it's easier to process. As mentioned, the IPv6 header is simpler than the IPv4 header. And if some of the extra features of IPv4 needs to be used in IPv6, there are extension headers that take care of that. These extension headers are chained one after another, so we can have multiple headers after each other. Here we have some examples. This is the most common situation that we see on the internet, is that we have an IPv6 header, and then just behind the header, we have directly the payload, which is here a TCP payload. That might be a web page. Sometimes we need to put in extra information for the routers on the way by using what's called a routing header. And here we have the first extension header being the routing header. So we have the IPv6 header. And then the next field in the IPv6 header is pointing to the routing header, which has the decimal number 43. And then the routing header has all its information that is being used by the routers on the way. And then that one points to the next payload, which is then the TCP. And that can be chained together. Maybe for some reason, the packet needs to be fragmented. In that case, we have the IPv6 header, we have the routing header, then we have a fragment header, and then we have the TCP payload. So this is how IPv6 does its extensibility. There are certain rules for these extension headers. For example, an extension header should not appear more than once. And the exception here is the destination option header, because there can be a destination option header for the routers on the way and for the end machine, and they appear in different places. But for example, the fragmentation header, that is not allowed to have two different fragmentation headers in IPv6. There's also a special hop-by-hop option header that needs to be read and being acted on by every machine on the way, every router, every switch, and so on. And that should only appear once, and it should be the very first header in the list, because it has to be used by every node. It should be very easy to access that. So the destination option, that is the one that can appear twice, and only twice. It can appear before the routing header and before the upper layer protocol. The first one before the routing header is some destination option for the routers, and the other one is a destination option for the end machine that is receiving the data. If we have destination option for there, it should be the last one in the list if it is used at all. So if there's just one destination option, it should always be the last one. And the fragmentation header should only appear once. So even if the packet needs to be fragmented more than once, we only have one fragmentation header, and it cannot be combined with the jumbo payload hop-by-hop option. Jumbo payload is to create extra large IP packets, and that contradicts the fragment header, because we do fragmentation if the connection doesn't allow large packages. So we don't want to have jumbo payload. And here's the list of the extension headers when they appear, or in the order they can appear. Remember, in the usual case, we only have the IPv6 header on the very top, and then the upper layer payload number 9 there, and all the ones in between are just optional and are usually not there. Very important, and a little change from IPv4, at least the way that IPv4 is usually used, is that IPv6 does path MTU detection, which means that IPv6 is probing the whole path between two endpoints and seeing and checking out the largest packet size that can go through that path. Also, while with IPv4, every router on the way is able to fragment a datagram, is, for example, able to fragment UDP or TCP on the way. That's not the case with IPv6. Only the sender is allowed to do fragmentation. So if a device on the way cannot handle the size of a packet, it will just drop the packet. It will not do the fragmentation on the way. That is an optimization because it makes routers much simpler than before. And it then will inform the sender that there is an MTU conflict, and it will also report the maximum MTU possible. And this is being done, the signaling back to the sender is being done via ICMPv6, packet-to-big message. So it's very important with IPv6 not to block ICMPv6, because if you do, you break IPv6 and it will not work. So here we have a graphical representation how path MTU detection works. The machine on the right side wants to send some data to the machine on the left side, and the two machines in the middle are routers. On the first hop, we have a maximum transfer unit of 8 kilobyte. Then in between the two routers, we have a maximum transfer unit of just 2 kilobytes. And then between the last router and the endpoint, the receiver, we only have the minimum allowed IPv6 MTU of 1280 bytes. So first, the sender tries to send packages with the size of 8 kilobyte, because that is the MTU of that link. Of course, that's not Ethernet, because Ethernet has an MTU of 1500, but maybe it's Ethernet with jumbo packages enabled, then it could be 8K packages available there. Because the upstream is just 2K, the first router will respond with an ICMP V6 packet to big to the sender, and the sender needs to start again, this time sending a 2 kilobyte large package. Now that gets routed by the first router, receives the second router, and that one detects that the upstream connection is too small, and it again sends back an ICMP V6 packet to big message to the sender. And now the sender is sending just 1280 byte packages, and they go through. And the sender machine will remember this information for a certain amount of time, and all the next packages will be just 1280 bytes. So the sender will do the fragmentation on that. Let's have a look on IPv6 addresses. Now, this is probably the most, the change in IPv6 that most people know about, is that IPv6 addresses are much larger than IPv4 addresses, so we have more addresses available. IPv6 addresses are 128-bit long, so that's 16 bytes per address. In comparison, in IPv4, we just had 32-bit per address. That is 4 bytes per address. And with every bit that we add to an address, the address space just doubles. So IPv6 has the really large number of addresses, which is 2 to the power of 128, which is equivalent to 340 billion addresses, or 340 undecillion addresses. That's a really large number. IPv6 addresses are written using 32 hexadecimal digits. And this is a situation where system administrators first fringe and say, why can't we use decimal numbers like in IPv4? Actually, using hexadecimal numbers makes totally sense and is much easier once you have some routine with that, getting the grip with that. Because with hexadecimal, you see actually the representation of the bits, and you can easier recognize patterns in the addresses than what is possible with decimal numbers in IPv4. So the 32 hexadecimal digits are arranged to 8 groups of 4 digits each, and they are separated by a colon. And there's an extra RFC 5952, that defines how IPv6 addresses should be displayed. So that is important for everyone writing software, and software that displays IPv6 addresses. So here we see the one IPv6 address in its full beauty. So these are 32 hexadecimal numbers in blocks to 4 numbers, and the numbers are separated by colons. What numbers? I see characters in here. I see A, B, C, and E, and F. These are certainly not numbers. Yes, they are. In hexadecimal, every number has 16 different values, and they are represented by the decimal numbers 0 to 9 and by the letters A to F. So 0 to 9 is just the same as in decimal. And then the letter A is actually the decimal number 10. And then it goes up to F, which is the decimal number 15. So we have counting from 0, we have 16 different numbers that we can use in an IPv6 address. If we have leading zeros in a group of 4 digits, then that leading 0 can be omitted. So that number you see here on the top, let me highlight that one. Makes it black, sorry. So the 2001 0db8 can be shortened to 2001 db8 colon. Same as in the middle where we have 0022, that can be shortened to just 22. So whenever we have leading zeros in a block of 4 digits, the leading zeros can be omitted. If we have a group of all zeros somewhere in the IPv6 address, one of these sequences can be replaced by just a pair of colons. Be careful, you can only do that for one sequence of all zeros, not twice. So here in this example, 2001 db8 100 000 and then 541 fa20, the 000 in the middle, which are 3 blocks, each 4 digits, can be replaced by just colon colon, and we end up with the IPv6 address at the bottom. This is really handy by when using some special addresses, such as the loopback address in IPv6, which has all zeros and then a 1 at the end, which can be written colon colon 1. If we want to denote networks, we use address prefixes in IPv6. We don't have network masks anymore. Here we see certain prefixes and how they are written. The first one is 64 network, which actually means that the last block here is an all 0 block. So fully written, that first IPv6 prefix would be 2001 0db8 0 and 100 0000, because the /64 has 64 bits, and every block of 4 digits in an IPv6 address is 16 bits. So there needs to be one more block at the end of that prefix. In the middle one, it's 2001 db8 /32. We just have 2 blocks filled here, which makes 32 bits. That's fine. And the last one is a /16, which is a rather large IPv6 network, which is usually given out to regional registries. The prefix written with / and then a number defines the number of important bits in a network from the start. So it separates the network ID from the host ID. So the prefix part, the part that specifies the network, is always the first 64 addresses in an IPv6 address. So in this case, it's the 2001 db8 100 200. That is the prefix, that is the network part. That is the address of the network. And then the last 64 bits, in this case, abacafe 23422, that's called the host ID, and that identifies the machine inside the network. And it's always that split. It's always the first 64-bit is network, the last 64-bit is host, which makes it quite easy to work with IPv6 because you don't have variable length networks in IPv6. Unlike with IPv4, in IPv6, we have certain types of addresses which are predefined in the standards. We have unicast, we have multicast, and we have anycast. Unicast is the typical one-to-one communication. Multicast is a one-to-many communication, one sender, multiple receivers, and anycast is one-to-someone communication. So one machine sends to some machine and doesn't care which of a group of machines receives. When we look at the unicast addresses, which are the one-to-one addresses, we have even more types in there. We have the global unicast addresses, which are the ones that are routable and usable in the whole internet. We have link local addresses, which are only valid in a single subnet. Once has been site local addresses, but they are now deprecated and shouldn't be used anymore. And we won't cover that in this webinar. We have unique local addresses, which are like the private IP addresses, but they are statistically unique. So they don't overlap, they don't collide with the private addresses some other company or other network is using. We have some special addresses that we see in the next slides, and we have some transition addresses that help with the IPv4 to IPv6 transitions. So here we see special addresses. One address is, for example, the unspecified address, which is all zeros, and we write that just : : and the unspecified address is, for example, used by a DHCP client, a DHCP client that doesn't have currently an IPv6 address. It sends out a query to DHCP, and in the field which has the requested IPv6 address, it puts the unspecified address in there and says, I didn't had an IPv6 address before, so just give me whatever is available. Another special address is the loopback address, which is : 1. One note here, in IPv4, we had a full /8 network for loopback. We don't have networks for loopback in IPv6. We just have the one address. However, nothing is really lost here. We can always bind some other prefix to the loopback interface and create as many loopback IPv6 addresses as we need whenever we need them. So just that they are not reserved and wasted before. So this is how global unicast addresses look like. Global unicast addresses always start with the bit pattern 001, which is either the number 2 or the number 3 in the beginning. So if you see an IPv6 address that starts with the number 2 or the number 3, that's a global unicast address. Then we have 45 bits of the global routing prefix, and that defines all the different networks that we can create from global unicast addresses. And then we have usually 16 bits of subnet ID used for subnetting inside a network. And that gives us 65,000 different subnets, and then the last 64 bits is the interface ID. So the interface ID, which defines or specifies the host, the machine, can either be built from the interface EUID64 ID, which is a 64 address that is being burned into the ROM or flash ROM of certain network cards. Or it can be created by a MAC address, which has 48-bit, where then the hexadecimal number FFFE is being inserted as the third byte of the MAC address. We will see that in a moment. It can also be based on the network, and then some algorithm is being used to create a hash, and then out of the hash, the IPv6 address, the interface ID is being created. That makes it very privacy preserving, but still stable on a single network. So the same machine will always have the same IPv6 address on the same network. It can be a random host ID that's used for privacy in public networks, or it can be set manual. Here we see how IPv6 host ID is being created from the MAC address. We see the MAC address on the top. One bit is flipped in the first digit, and this is because that one bit in the MAC address tells us that this is a user-defined MAC address, and that allows the user to create a MAC address for a network card that has many zeros, and then these zeros will be then collapsed with just : in the IPv6 address. So that allows the user to still create IPv6 addresses from MAC addresses, but have some influence in how the IPv6 address then looks like. Why the value FFFE? Turns out if you have a MAC address and you insert FFFE, the checksum of the MAC address is equal to the checksum of the host ID created. So that makes it easier to calculate the checksum on both MAC addresses and IPv6 addresses, because network cards only need to do that once. About linked local addresses. So we have heard about global addressing, which are the addresses that are freely routable in the internet. And the linked local addresses are special in that case, that they are only valid in one single subnet. And linked local addresses always start with the hexadecimal numbers FE80. And then all the 54 bits that are remainder of the prefix of the IPv6 address are all zeros. And then we have the interface ID. And the interface ID is usually created from the MAC address. So these linked local addresses, they are used for communication of hosts on a single link. That is, all the hosts that are directly connected by an Ethernet cable or connected via a hub or a switch. There's actually quite a lot of communication that happen over linked local addresses in IPv6, such as local name resolution or the neighborhood discovery, which is the replacement of ARP, the address resolution protocol that we had in IPv4. And there's a couple of other stuff that is going on, like router to client communication, router advertisements, router solicitation, messages, and such. So the linked local addresses are quite important for IPv6. So the prefix for these linked local addresses are FE80, and it's a /10 network. And IPv6 routers never forward these linked local addresses. They are only valid in a single link. And you can think of them similar to the IPv4 APPA addresses, the automatic private IP addressing, which are starting with 169.254, which you see on an IPv4 enabled machine that doesn't have DHCP, or that does have DHCP, but there is no DHCP server in the network. Sometimes on some machines, the linked local addresses are the same on every network card. For example, this is true for Oracle Spark servers or older Sun Spark servers, because there the MAC address is actually in the firmware ROM and not on the network card. And every network card in a Spark machine might have the same MAC address. Now, usually that is not a problem because every network card is in a different subnet. And if you do trunking or bounding or something like that, then it's a different story, but normally it's not a problem. However, if we have such a configuration, then must be a way for the operating system to distinguish the different network cards. So which one do we use when we send out packages? And this is where zone IDs come in. Every network card in an operating system, might it be Windows, might it be macOS, might it be Linux, or one of the BSDs, every network card has also a zone ID. And the IPv6 address, the linked local address, together with the zone ID, is being used as the selector for where we send out data. And here we see an example. The machine in the middle, this one might be one of the Spark machines. And you see it has exactly the same IPv6 linked local address, FE80:2:ED54 on both sides, on both network cards. And if this machine wants to talk to one of the other machines that we see on the top, the operating system doesn't know where to find that machine. should I send the packages out on network interface card 1, or do I need to send out the packages on network interface card 2? For that reason, when we use link local addresses, we always have to specify the zone IDs together with the IPv6 link local address. For example, if you want to ping with link local addresses, that is possible, but you have to specify the zone ID. There are some operating systems when you don't specify the zone ID, the packages will be just sent out on all network interfaces, and that might not what you want. Here we have an example of a zone scope ID from a Mac system, and it's similar on the BSD. And there you see in the second line, at the end of the second line, or in the second line, you see the link local address, the FE80 address of that machine. And after the IPv6 address, you see %EN1. And for macOS, that is actually the zone ID. So it's the name of the interface. For Windows, it's different. Windows uses some unique identifier for the network cards, and you have to specify the unique identifiers there. And there's also the scope ID, 0x5, which also can be used as an identifier when sending out packages on a link local address. But the zone ID, the percentage network card, or on Windows, the UUID of the network interface is the most popular one to use. Another type of IPv6 addresses that we see are the unique local addresses, or ULA addresses. And these are the private addresses. These are the counterparts of 192.168 or 10/8 network addresses in IPv4. The unique local addresses always start with the hexadecimal numbers F and D. And there's one bit that decides whether the address is locally assigned or whether it is globally registered. Because there is currently no global registry for these unique local addresses, all unique local addresses currently being in use are locally assigned. So that bit is also always set to 1. It might change in the future, but for now it's always set to 1. So that makes the F and the D as the first numbers. Then we have 40 bits of global ID, which is a random number, which is generated in a way that guarantees statistically that that number does not collide with some other network and some other company using unique local addresses. Then we have 16 bits of subnetting, which gives us 65,000 subnets that we can use in our network. And then we have the 64-bit interface ID, as we have with all the IPv6 addresses. Now, the unique local addresses, they are local addresses. So they are local to a private home or to an organization, yet they are statistically unique, meaning that if two networks merge, there's a very low probability, if both networks have ULA addresses, that there will be address clashes, which is unlike with IPv4. When two companies merge their networks, nowadays, it's very, very likely that they have used the same private addresses. Possibly they have all used 10/8 addresses. So when they merge, they have to really redesign their network. They have to renumber one part of the network, which is the big pain. In IPv6, you don't have these problems. You can use local addresses, private addresses, but still, these addresses are unique. So if you merge with another network, you don't have any collisions. So the ULA addresses have the prefix FD00, and it's a /8 network. Also, the ULAs have a global scope, but no scope or zone ID, and they will not be routed in the internet because they are private addresses. And then we have multicast addresses, and multicast addresses always start with the hexadecimal numbers FF. So if you see an IPv6 address starting with 2F, then you know that's a multicast address. Multicast is a one-to-many communication, so one sender and multiple recipients. The next bits, the next 8 bits, we have 4 bits of flags and 4 bits of scope, more on that later. And then we have 112 bits of the group ID, which is like a subscription number. Every recipient can subscribe to a multicast address by selecting a group ID, and will then receive all the packages that are sent to that group ID. IPv6 uses a lot of multicast for internal services. There's no broadcast anymore, only multicast. And that makes IPv6 much more well-behaved than IPv4. For example, in IPv6, you can have more than 10,000 machines in one subnet. It's not a problem at all. In IPv4, that doesn't work. It doesn't work because in order to find IP addresses in IPv4, we use ARP, and ARP is built on broadcast. So with a broadcast, one machine is shouting into the network asking who has IP address X and Y, and that will wake up all network cards in the network, and they all have to process that request and see if they are meant and if they have to respond on this. If you have a certain number of IPv4 machines in a subnet, you just have too many broadcasts. The machines are completely busy just processing the broadcast, so that doesn't scale very well. With IPv6, we don't have that problem because of multicast. Only 1 or maybe 2 or 3 machines are being woken up if there's an address resolution happening, and not all of them that are in the local link. So IPv6 is much more well-behaved than IPv4. So these are the multicast address flags. The only one that is really of interest here is the first transient flag, whether that multicast address is one that is assigned by IANA, so there's a global registry, it's a well-known address, or whether it is a transient address, or we can also say it's a local address, something that is not globally registered in the internet, something someone has just decided to use. So the whole number range for multicast addresses are cut in half. One half is reserved for permanent addressing. The other one is reserved for just free-form addressing. And anyone can come up with a transient address and can use it. And then we have the address scope in a multicast. And that determines on what level, on what scope the multicast addresses are being seen, the multicast traffic is being seen. Number 1 is just an interface local. It's just multicast on the same machine, on the same server, for example, if we have a cloud server. If you have a cloud server with containers, then interface local multicast could make sense to have communication between different containers, but all containers using the same network interface. Then we have link local, that is only on the local link, all machines directly connected to the same Ethernet. Admin local and site local and organization locals are different scopes that can be configured in routers. So an organization can decide what scope an admin local, a site local, or organization local multicast should reach. Usually admin local is for administration tasks. Site local is just one location or one office building, for example. An organization local is then the whole network of a whole organization. And E is global, it's the internet. Everyone can possibly reach and receive that multicast traffic. And here we have some examples. This is a node or interface local scope. We have the all nodes address. We can use that to send messages to all machines, all containers on one node. And if some of the containers are routers, which could be, we can address them with the old routers address. And then there is the Multicast DNS V6 address. That is for serverless multicast DNS name resolution. Similar we have on the link local scope, but more, we have the all nodes and the all routers address. The all nodes address can be used to address all the machines in the network in a link, a single link. All routers, again, goes to all routers on the link. We have, again, multicast. We have universal plug and play devices. We can access the link name, which is actually a way to do DNS-less name resolution for networks. We can receive all DHCP agents, which are relay agents in routers. We can have link local multicast name resolution from Microsoft. We can ask for network time without specifying a specific network time protocol server, just asking for FF01::101. And that will be received by all NTP servers that are in the local link. The solicited node address is something special that is used for the address to MAC address, IP address to MAC address name resolution. And I will talk about that in a moment. And then there is the address for the the node information queries. And that can be used to create the host names and other IP addresses, even IPv4 addresses from a machine. And here the examples that are available for site, local, or variable scope. So about the solicited node address. The solicited node address is the magic that allows IPv6 to well behave with the MAC address to IPv6 address resolution. Every machine that is connected to a network, every IPv6 enabled machine has the solicited node multicast address. And that address is built from the solicited node multicast prefix, which is FF02:1:FF0:0/104. And the last 24 bits of that address are taken from the MAC address. And I have that here in a graphical representation. We have the interface ID, which is or which could be derived from the MAC address, which will then be the last 24 bits from the MAC address, or it will be the last 24 bits from the IPv6 address. And that is then taken over to that multicast address. And whenever an IPv6 machine needs to find out the MAC address of another machine, it sends a multicast request to that solicited node IPv6 address, and it can calculate that from the target IPv6 address. It just takes the last 24 bits from the target IPv6 address, sticks it on the solicited node prefix, and then sends out a multicast. And as long as there are no collisions on the last 24 bits, only the machines that have the same last 24 bits will be woken up and have to process that request. And in typical networks, that is just one or maybe two machines. So that is very lightweight. And then we have a couple of special addresses like transition addresses. The ones were the IPv4 compatible addresses with all zeros, and then the IPv4 address in the last 32 bits that has been deprecated and has been replaced with the so-called IPv4 mapped addresses, which are all zeros, then FF, and then the IPv4 address in the last 32 bits. When we write these kind of IPv4 mapped addresses for humans, then the last 32 bits are be written in decimal conversation the same way as we do with our standard IPv4 address. So we have a mix of IPv6 in the first bits, and then IPv4 in the last 32 bits. And then there are certain transition addresses which are reserved for certain transition technologies, 6-to-4 addresses or isotope addresses. However, as we have seen in the beginning of this presentation, these transition addresses are not really in use anymore. They had been in use 20 years ago when there wasn't enough native IPv6 in the world, but nowadays we have a lot of native IPv6, so there isn't really a need to use 6-to-4 or isotope anymore. And there's the special address for documentation. So if you write documentation and you want to give an example and you need an IPv6 address, you use an IPv6 address that starts with 2001 DB8 //32. And that is the official IPv6 documentation address that is guaranteed to never be used in the internet. It's reserved for documentation purposes only. So, and that finalizes the IPv6 fundamentals part. Do you have any questions before we jump into DHCPv6? All good? Or someone is asking the most important questions while being muted.
I have one question, maybe not directly related to this, but you said mentioned earlier that there was statistically not much chances of collisions, for example, when merging together two networks, like for mergers and acquisitions.
Yes, with the unique local addresses, that is, yes.
Yeah. So would does that mean that, for example, if you had companies with just IPv6, or let's say if IPv6 usage would become very widespread, that there would be less or even no need for address spaces like we have in our solution?
Yes, exactly.
Okay, yeah.
That should be a thing of the past, or
yeah.
a thing of IPv4 only.
Yeah. Of course, while we still have IPv4, we would need it there, because you can have, servers and objects that have a mixture of IPv4 or IPv6. But I was thinking sort of in the future that would not make sense.
Yes.
Yeah.
And I can also envision that companies that merge nowadays, if they face the choice of either renumbering half of their network or switching to IPv6, that they choose the later. Yeah. Because it's roughly the same amount of work.
Yeah, exactly. Yeah, it's interesting. Another question, also maybe not directly related to, well, it is related to IPv6. Sort of in our solution, we are reading in lots of IPv6 addresses, like from cache, etc. On routers. Does it make sense? Does it make sense to do like a very early filtering on what addresses we are reading into the solution? Because, like you say, there are different classes and there are different types of addresses, maybe, or even some addresses that we should not be saving to the database or storing. Maybe just keeping it. Are there some addresses that are only valid for a really short time, and once we had it in the system, it becomes redundant?
Yes, there are such addresses. Unfortunately, these are the privacy addresses, and I cover that a little bit in the DHP part that is upcoming.
Okay.
However, unfortunately, there is no easy way to filter them. There's no easy way to do that because they look the same as non-temporary addresses, as stable addresses. The only difference is that the temporary addresses just change like every 24 hours.
Okay. Yeah.
And they are privacy temporary addresses meant to not be stored anywhere. Yeah, that might be something we would like to discuss in more details, if there is a way to filter them out. Because if you have a large network and you read in these addresses, that can be a lot of addresses that are not of real use.
Yeah, exactly.
Anywhere.
Yeah. Or if you have, like in our case, we're reading we're reading and saving, millions and tens of millions of addresses maybe into the database, and if it's not really beneficial, or it would just make sense to read them when you need them or store them in memory or something. But yeah, it's out of the scope for this talk, but it was something I've been thinking about.
Yeah, one thing that I can think of is to mark addresses once they are seen first time, to mark them as potentially temporary addresses, and if they are not seen after 24 hours anymore, or some period of time that can be configured, they will be then removed from the database.
Yeah.
Only addresses that are seen longer than 24 hours are possibly stable addresses and possibly are of interest.
Yeah, that makes sense. So maybe you even have like a counter or a bit that you flip.
Yep.
Yeah.
How often in a certain time period the addresses have been seen.
Mm-hmm. Yeah. Okay. No further questions from me, at least.
Okay. Anyone else?
Is there any country that has gone full-blown into IPv6 yet?
I mean, there are some countries that have over 50%
Okay.
of IPv6 traffic, but there will always be IPv4. So we will never see 100% only IPv6. There will always be islands and parts of the network just IPv4.
Mm-hmm. But I mean, global traffic in, I mean, not within the company, but I mean, between companies or the
I think
network.
on the Google sees on their mail servers, they see about 60 to 70% IPv6.
Okay.
So mail traffic between mail servers is very much IPv6, but this is possibly just 2 handfuls of big players. Facebook, Microsoft, Google, maybe Yahoo, and who else is doing email today?
Not many, I think.
Yeah.
But which countries are leading?
India, Greece, Germany, and US, I would say. US is 46%, Germany is 55%, India and Greece is 57%.
Okay. Okay, thanks.
Good, then let's continue with DHP V6. So in this talk, we have the comparison between DHP V6 and DHP V4. We talk about DHP V6 high availability, and we look at some of the popular or not so popular DHP V6 servers out there. So about DHP V6. From a bird's eye view, DHP V6 works very much the same way as DHP V4. But in the details, that is the implementation, it is very different. It's not an upgrade to the old DHP V4 protocol, but it's a new protocol of its own. Reason for that is that DHP V4 already was an upgrade from Dhp. And Dhp V4 has a lot of legacy stuff in there that is not really good and smart. And all this legacy stuff has been not implemented in Dhp V6. So it's a clean start, so to speak, of the same idea. Another difference is that Dhp V6 is a complete layer 3 protocol, and that is possible because every IPv6 capable machine already has a link local IPv6 address. So we already have IP communication. We already have an IPv6 address. It's only a link local one, but we can use that to talk to our router. So we can reach the DHCPv6 relay in the router. That's different from IPv4. DHCPv4 must work on a machine that has no IP connectivity at all. So writing a DHP-V4 client is much more complex because you have to somehow convince the network stack of your operating system to send raw Ethernet frames. And you have to create raw IP packages from the Ethernet frame because in IPv4, at that point of time, there's no IP address. So the operating system cannot do that. So DHP V6 is much cleaner and there's much better separation of the layers there. There's no low-level kernel trickery required. It works on different port numbers. The servers and the relay agents listen on port 547, and the clients listen on 546. Both is UDP based. The communication happens over multicast. And there is an all DHCP relay agents and servers multicast address, which is FF02:1:2. And FF02 tells us, the FF tells us it is multicast. The O2 tells us this is link local scope. So these are multicast traffic addresses that only work on the link local network subnet. So these communication is then picked up by a DHP V6 forwarding agent and is then sent to the real server via Unicast. There's also an all DHCP servers site local multicast address, which is FF05:1:3. That is actually seldomly be used because it requires that you have multicast routing between the routers in the network. And most companies nowadays don't do that because it's an extra complexity. And you don't do that only for DHP V6. The role of the routers is special in DHP V6. DHP V4 works even without routers. If you stick an IPv4 client in the network and that client can do DHP V4, and you directly connect that machine with an Ethernet cable to a server, and that server is a DHCP server, it will request a DHCP address. In IPv6 with DHCP V6, the initial information that DHCP V6 is required in the network comes from the router. So there must be a router telling the clients, hey, we use DHCP V6 in this network. And that happens with the so-called M flag and the O flag. The M flag stands for managed flag. And if the M flag is set from the router, it means that clients have to get the IPv6 address from DHCP. The O flag, O stands for other configuration items. If the O flag is set, that means the clients need to request other network configuration data, such as DNS, resolver addresses from DHCP. The default gateway addresses will always be retrieved from the router and never from DHCP. That's also different. In DHP V4, we have an option that configures the default route for a client. Not so in DHP V6. In DHP V6, it's also always the router that gives it, which is more natural because the router knows best where the default route is and whether the router is actually the recipient of a default route. So that's the natural way to distribute that information. While the DHCP server might not be aware that a router is being switched in the network. Here we have the network communication between a Dhp V6 client and a Dhp V6 server. In this case, we have in the middle a router with a Dhp V6 relay agent. We have one DHP server on the top, and we have another DHP server on the bottom. And it starts with the client sending a router solicitation message. And that message usually is being sent after the machine starts up, and it asks the network, do we have any routers in this network? And if there's a router, that router responds with a router advertisement telling, hi, I'm the router. I can be your default route if you like to. And it might include the MNO flags. And if there is an MNO flag, the router tells the client, this is a network with Dhp V6. Please enable Dhp V6. The operating system listens on these router advertisements. And if it sees an MNO flag in there, it starts the Dhp V6 processing. Now, the address allocation in Dhp V6 is or can be different from Dhp V4. In the original Dhp V6 specification, the RFC, it was even mandated that Dhp V6 server should always issue IP addresses randomly from the available pool to make implementation of Dhp V6 servers much easier, especially if these servers are small router type servers in home equipment that might not have a storage. Nowadays, with the new standards, it's just a should or could that IP addresses should and could be given out randomly from the address pool. But if a DHP server gives out addresses randomly, then together with the large number of address space we have, it's much harder to guess an IP address or scan a network segment. Also, as we see later with the high availability option, with that, it's possible to run two DHCP servers in kind of a failover mode without having any communication between the machines. In Dhp V6, a client can request different allocation types. It could be a non-temporary address. A non-temporary address, it's an address that if the server has that address free, it will always give the same address to the client if available. So this is very similar to a Dhp V4 address request. Then a client can request temporary addresses. And the temporary address is an address that will always change on each address and has a very low lease time, usually less than 24 hours, sometimes even an hour or even smaller. This is used by clients for outgoing connections. So if you have a client, Linux, Windows, or macOS, you will probably see that the machine is requesting a non-temporary address, a stable address, and also one or more temporary addresses, and will then use the temporary addresses for outgoing traffic. Reason is here to prevent outside machines, outside organizations to track the users by looking at the Ipv6 address. A client can not only request one address, a client can request multiple addresses. So a client can ask, oh, give me please DHCP server, give me 4 non-temporary stable addresses and give me 10 temporary addresses. And because the Dhp V6 server has a large number room and have that numbers, these addresses free, it will usually just comply and respond with that addresses. So for example, on a server type machine that uses Dhp V6 for addressing, like on a cloud machine that can spawn up containers, it could be that the operating system or the cloud management system will just request a number of addresses, like 64 stable addresses when starting up, and will just give that on demand to the containers whenever they launch. And now we have prefix delegation. And with prefix delegation, a client that is usually a router itself can ask for a whole network prefix from an upstream server. And that allows for a hierarchical Dhp V6 configuration. I will cover the prefix delegation and what can be done with that a little bit later. But this is one important difference from Dhp V4, that in Dhp V6, we have this different kind of address requests. In Dhp V4, we only had one type of address request, which was the stable address. And here, a client can request different types of addresses. IPv6 also supports stateless automatic address configuration, which is a way to get an IPv6 address without a DHCP server. Basically, with Slack, the routers, they announce the network prefix into the network, and also with a flag, tell the clients that the clients can just randomly select an IPv6 address from that prefix. Slack can be used as an alternative to Dhp V6, but it can also be combined with Dhp V6. And with Dhp V6, we have two different options to get an IPv6 address to a device. We can have stateless configuration. And stateless configuration means we have no state on a server somewhere. There's no state on the DHCP server. There's no database in the DHCP server. With stateless configuration, usually the IPv6 address is being created from Slack or manual configuration. And then just the other network configuration, like the DNS resolvers addresses, NTP server addresses, and such, will be received by DHCP. And the other option is having full stateful configuration, which is similar to Dhp V4, where the server has a database and needs to store the state of the release. So the server needs to know which MAC address or which client identifier has been used with an IP address, so that if that client comes back, asks for renewal, it will get the same address. So stateless configuration is we use the DHCP server together with Slack. The IPv6 address will be received from the router. And with stateful configuration, IPv6 address will be received from the DHP V6 server. And in both cases, additional configuration can be retrieved by DHP V6 as well. Back to our picture here. Our client now knows that it is in a DHP V6 enabled network. So it sends a DHP solicit message, actually asking, is here any DHP server? And that request is a multicast request that is being received by a local DHP server on the same link. It's also received by a relay agent in the router. And if it is received by the relay agent in the middle, that one will forward with a relay forward message that to configured DHCP servers. Then the servers, they answer with an advertise. So they allocate an IPv6 address, they reserve that IPv6 address, and they send an advertised message to the client. Both of them send an advertised message advertising a different IPv6 address. The client is then in the so-called selecting state, and it selects one of the advertisements. And usually it goes with the faster one, the one that sent the advertisement first, which is in our case the one on the local link. So the client sends a DHP request, which is a unicast UDP over link local addresses, sends that to the DHP server, and then the DHP server replies and confirms that the IPv6 address can be used. And then the DHP server configures the new IPv6 address, which in our case is the global routable address, so it can now go out to the internet because that address is routable and can reach the other networks. because a DHCP server can have multiple IP requests from the same clients. The server can have requests for temporary addresses, can have requests for prefix delegation, can have requests for stable addresses. The server must somehow be able to distinguish between all these different addresses given out to the same client. And that is being done by the so-called identity association. And the identity association is a number that is generated by the DHCP server and is being sent back to the client. And it's also recorded in the database. And that is being used to associate the configuration information to the client and to a specific request of the client. And whenever the client requests the same information again, it will send the same identity association ID with that. So that is used, the identity association is used to distinguish between temporary addresses and the non-temporary addresses. Here in this picture, we have an overview of the different client states a client goes through when doing a DHP V6 communication. A client that just starts up and having no global routable IPv6 address, just the link local address, goes into the init state. And from the init state, it sends a solicit message, and the server answers with an advertise message. There could be multiple servers, so we can have multiple advertise messages. And now the client is in the so-called selecting state. It selects one of the advertisements and requests the address with a request message, which the server will then confirm with a reply message. And we then say that the client is in the bound state. The client has an IPv6 address for a given lease time and can work with it. Then after a certain amount of time, usually 50% of the lease time, the client goes into the renewing state. And in the renewing state, it tries to renew the IPv6 address that it currently owns and which is still valid for half of the lease time. And if the client, if the server is still there and the server still is allowed to give out that IPv6 address, it will then confirm that IPv6 address with a reply, and the client goes into the bound state again. And in the normal case, the client will then go between the bound state and the renewing state every 50% of the lease time. If for some reason the server will not answer anymore, because that server has been replaced, then after 75% of the lease time, the client will go into the rebinding state. It will send a rebind message, and it will send that rebind message to all DHCP servers, not only to the one DHCP server that originally gave out that IP address. So the rebind message basically says, is there any server here that can confirm this IPv6 address, that I can use that IPv6 address any longer? And if there's another server that can confirm that, because it's a backup server, for example, then that server will send a reply and we go into the bound state again. And everything is good and the client has the IPv6 address again. If for some reason there's no response from any server at all, then the client will lose its IPv6 address. It will go back to the init state and will start the whole cycle again. So it will send out a solicit and wait for an advertise. Compared to IPv6, there is a special mode in DHP V6 called rapid commit. And rapid commit is especially designed for mobile devices like mobile phones or tablets. These network devices should be able to quickly join a network. And the normal DHCP communication between a client and the server is a two-way handshake. So it's two-way because first the client requests an address, then the server advertises an address, then the client asks for acknowledgement of that address, and then we get the acknowledgement from the server back. So it's 4 packages back and forth in the packet exchange. That can be speed up with rapid commit, and then there's only 1 packet exchange. With rapid commit, there's no information sent back to the servers telling the server whether the client is really using the advertised addresses. Basically, the client is asking, can anyone give me an IPv6 address? And then all the servers answering, oh yes, here's an address you can use. But the servers will never get information if the client actually have used that address. And every DHCP server must then reserve that IPv6 address for the full leased time. Now, this seems to be using much more IPv6 addresses than needed, and that's true. So there's a lot of IPv6 addresses being allocated and reserved, but not really in use. But that's not a problem because the IPv6 subnets, the /64 prefixes, are so large that we don't really care. And here's the communication with client having rapid commit. So the client sends a solicit with rapid commit option, asking, can anyone give me an IPv6 address? And then the servers send a reply back, and the client will immediately use that IPv6 address. Both the servers need to store the IPv6 address given out, even though only one of the IPv6 addresses given out is being used. The other one is just blocked. However, that makes it very fast for a mobile network client to join the network. So I've already mentioned prefix delegation. And with prefix delegation, a server can distribute whole network prefixes to clients. And clients usually are other routers, DSL CPEs or cable CPEs, or other downstream DHCP server. For example, here in my network in Germany, my provider is giving my router by prefix delegation a /48 network. And then my router can split that up into 256 smaller /64 networks that I can use here in my home network. It can also be used inside a company's network, so that a central DHCP server in the headquarters distributes all the networks to all the subsidiaries and all the other locations of that company. And if there's a change, only the main DHCP server needs to be changed, and then the changes will trickle through the hierarchy. Here's an example. The Dhp V6 server on the top delegates a /56 network, and then that server delegates smaller /60 networks. And there's even another router that then splits up the /60 networks for smaller /64 networks. Let's have a look at high availability options in Dhp V6. So DHCP is a critical resource in most networks, and if DHCP service is down, machines or computers might not be able to join the network. So we like to make DHCP service redundant and highly available. And we have multiple options here. With Dhp V6, we can actually do a split pool or shared pool. And with that, we have just multiple Dhp V6 servers, and they give out the same subnets. And because the IPv6 address space of a /64 subnet is so large, the statistic chance of address collisions is so minimal that we can do that without having any synchronization between the servers. And even if by chance there is a collision, which maybe happens every 100 years or so, statistically, in normal network, then duplicate address detection, which is built in every IPv6 stack, will just recognize that, and the client will then select a different IPv6 address. This does not work with Dhp V4 because the address space in IPv4 is just too small. We can't do these tricks in IPv4. So first we look at the split pool. We can just split 1/64 in 2 halves. That is still 2 billion addresses per, or 2 billion times 4 billion addresses per pool. That is still large enough for every network, and the pools are not overlapping, so it's impossible that 2 Dhp V6 servers will return the same lease for the same client or for different clients. And if one of the Dhp V6 servers stops responding, then the client will receive a new lease from the remaining Dhp server after lease expiry, that is. And here we have how that works. So at the bottom, we have 2 DHCP servers. They don't talk to each other. They don't have a high availability protocol running. They could even be different products. So one could be a Kia DHCP, the other could be a Microsoft DHCP. And by configuration, the pool, which is the 201 db8 100 0, that is split off into 2 different parts. Another option is the shared pool, which is very similar to the split pool, just that we don't split the pool. Instead, we have the pool on both servers configured, the full pool. This works best if the Dhp V6 servers allocate new addresses non-continuously, meaning random or hash-based. The Kia DHCP server doesn't do that at the moment, but it's planned to implement that later on. The IC DHCP server does that. The IC DHCP server does random allocation. Because the /64 subnets are so large, the chance that a server gives out the same address twice, or the different servers give the same address twice to different clients, is statistically very, very low. So it's 1 in 100 years occasion. And if they would do that, IP duplicate address detection will cover the edge case. And this is the configuration for such a shared pool. So we have 2 servers, both have the exact same configuration, which makes even deployment of these servers very easy because they can have 100% the same network configuration, pool configuration, and DHCP server configuration. You can just clone them. Something that is also possible in IPv4, but also makes sense in IPv6, is to have pure static DHCP, so no pools, only reservations. Every client's IPv6 address is bound to a client ID or a MAC address in the DHCP server. And then that configuration is being provisioned on 2 or more DHCP servers. And they all have the same reservation configuration. So no matter which DHCP server the client is asking, the client will always get the same IPv6 address and the same configuration. So this solution requires an out-of-band synchronization for the reservation, such as through the Men&Mice suite or Maestro. And this could also be done on the database level with a shared host reservation database. So having multiple DHCP servers accessing the same database, which works best with external databases like SQL databases with Kia DHCP or the Microsoft DHCP. And here we have the picture showing the reservation. So we see 2 DHCP servers, and both have the exact same DHCP configuration. Now, this picture here shows IPv4, but it works the same way with IPv6. There's no difference. Another option is to have a shared database. So we have pools and we give out addresses from the pools, but then we synchronize multiple DHCP servers via the database. And it could be that one or more DHCP servers just are connected to the same logical database, or that the database itself is made high available, so it's clustered, the database, on multiple data centers. Important here is that database locking can lead to a performance degradation if it is a high performance DHCP server with a lot of requests. And this picture shows the setup with two DHCP servers accessing the same pool database. And then we have true high availability, like the Kia DHCP that offers a high availability hook. And inside that high availability hook, we have even different operation modes. We can do load balancing, we can do hot standby, and we can do passive backup. And I cover that just now. If we use load balancing mode, we have two DHCP servers which are both active, and they both respond to lease requested. And the lease information is then synced between the Kia DHCP servers with the high availability plugin. In Kia, the pools must be split 50-50. So it's very similar to a split pool configuration, just that if one server fails, the other server has all the information and can give all the machines, all the client machines, the same Ipv6 address. And this is a setup with Kia DHCP in a load balancing mode. Then we have the hot standby mode. And in hot standby mode, we have, again, two or more Kia DHCP servers, but only one is active at any point of time. And the other one is just the hot standby machine. The hot standby machine receives all the leased database updates, but it's not serving any clients. And if the secondary, the backup server detects a failure of the primary server, it then starts responding to all the DHCP queries it receives. So this is the example of the hot standby mode. So why should anyone use hot standby mode instead of load balancing? It might be easier for management and for doing troubleshooting, because in the hot standby mode, you have just one active DHCP server. So at any given time, you just have to look at one machine when you do troubleshooting, for example. If you have a load balancing setup, then it could be that any of your DHCP servers respond to a client, which makes it a little bit harder to do troubleshooting in Dhp V6. So there might be good reasons to have hot standby. And then we have the backup servers. And Kia DHCP supports any number of backup servers. And these backup servers, they receive the leased database updates, but they are not an active part of the high availability setups. And backup servers are additional, so they can be deployed in addition to all the other high availability modes. So you can combine them with hot standby or load balancing. And here we have load balancing in addition with one backup server. And the backup server, one reason to have that might be that the backup server is for continuous for disaster recovery operation. So it's too far away, that backup server, to serve normal traffic. So we won't have him active at normal times. But if the main data center burns, like happened this night in Strasbourg for OHV, then all the data is still back up in the data recovery or data backup data center. And the whole network can maybe switch over to that, and the backup server is then configured to be an active server. However, the backup servers will never automatically become an active server. It requires an administrator to go in the configuration and change the role from a backup server to an active server. So this was the passive backup server. Also, newer versions of Kia, the active server, they don't need to wait for an update confirmation on the backup server, so that reduces the latencies compared to other high availability modes. Backup servers might also be interesting for network management solutions like Maestro, because it would be possible to retrieve data, just read DHCP data from these backup servers without having an agent or having any kind of communication with the in-production service. And here is an example of a passive backup server where one machine is operating in an active configuration, and it updates the second server. But the second server will not become active automatically. It requires the administrator to go into the configuration and change the backup server to become an active server. And in this case, also to change the relay agents to point to the backup server. So we are almost through. In the last chapter, I would like to tell you a little bit about Dhp V6 servers that are available nowadays. Still very popular is the IC Dhp V6 server. The IC Dhp server supports Dhp V6 since version 4. The current version is 4.4.2. The IC Dhp server is currently in kind of a maintenance mode, so it will not receive new features. It will only receive bug fixes, because IC is also working on Kia DHCP, and Kia DHCP is where all the new development happens. And at some point of time in the future, IC Dhp V6 or the whole IC Dhp package will be marked as deprecated and will shut down at some point of time, or development of that software will shut down. Kia DHCP is the new kid on the block. It's a successor of IC Dhp, and it was designed for Dhp V6 and Dhp V4 from the beginning. It also supports modern standards like Dhp V4 over Dhp V6 that you need if you want to sunset Ipv4. Also, it has the high availability support with the high availability hooks for both Dhp V4 and Dhp V6, which are not available in IC Dhp. Then there's the Microsoft DHCP server. Dhp V6 is supported since 2008 R2, and high availability can be done via the Microsoft server cluster. So you cluster a Microsoft server operating system, and then you install a DHCP server on top of that, and that makes the whole system high available. So there's no dedicated high availability mode or configuration for the Microsoft Dhp V6. Dhb V6 was a very capable, or still is a very capable Dhp V6 server for Linux, macOS, and Windows. However, the main developer of that server, Thomas Moralski, is now the head of development at ISC for the Kia DHCP server. So there is no new work on Dhb DHCP, but it still receives minor updates from the community. I just looked at the GitHub repository, and there were few changes, bug fixes in the last weeks. So there's still something going on, but possibly not new features coming in there. The white Dhp V6 server was the very first available Dhp V6 server. It was part of the CAME project, which was the very first implementation of Ipv6 for Unix at that time in the 1990s for BSD Unix. That development has stopped. While you can still find the white Dhp V6 server in the repositories of certain Unix operating systems, I won't recommend using that because it's not further developed. Dhp Pi6D is a Dhp V6 server written in Python, still actively maintained, and it's very easy to extend. It's possibly not very performant compared to Kia or IC Dhp, but I haven't tested that. But yeah, it's Python, so it's easy to hack on that and write your own extensions. So if you need a DHCP server that you can mold and turn into a thing that you want, this might be a good idea. Might also be nice for prototyping. Then there's the UDHCPc, which is Dhp V4 and Dhp V6 server for embedded system. It's now part of BusyBox. This is a very stripped down DHCP server that is used in embedded devices. And there's Jargonet DHCP server, which is an open source DHCP server written in Java. Still actively maintained, it's open source. And this is maybe a good choice for people who don't like Python, but like Java and want to tweak their DHCP server. And relatively new is Core DHCP, which is fast and multi-threaded modular and extensible DHCP server written in Go language. It's currently in development, so it's not feature complete. It has a modular design and you can write your own plugins in Go. And this would be my project where I would go if I needed a DHCP server to hack on, because I like Go more than Python and Java, and I think performance is possibly better there than with Java and the Python one. And we find Dhp V6 in router hardware. So many Dhp IPv6 capable router devices like Cisco and Juniper and Broadcom and so on, they include also a very basic Dhp V6 server in their offerings. And with that, I'm done with Dhp V6. Do you have questions?
Two questions, Carsten. First one, you said when you were promoting the backup server, you would need to change the relay agent.
In the one picture I had where, let me go there, in this picture here.
Yeah.
Because in this picture, the relay agents only point to the active DHCP server. So they only have the relay agent configuration only points to one server, because the other server is not active, it's just a backup. In all the other pictures, like here, the relays have been configured to send all the requests simultaneously to all the DHCP servers that are active.
Okay, so it's not using the local link DHCP address to communicate.
No, the link local addresses are being used on the top between the clients and the relays.
Okay.
But the communication between a relay and the server is unicast, just unicast IPv6, and it could be over multiple networks. So in that case, there are IPv6 addresses that are configured in the routers that are relay agents. It's very much the same as in Ipv4 with Dhp V4.
Right.
So it could use a multicast, the site local multicast address, but that would require having multicast routing configured.
Okay. The other question was the duplicate address detection in IPv6. How does it work?
It works by the client receives an IPv6 address, and before using that IPv6 address, it will send out a solicit node request. So it will do what in IPv4 would be an ARP request. Ask who has this address. So it only receives that address itself, but it then, before using that address, will ask the network, does anyone know who has this address? And if there's no response, then it can be certain that nobody is using that address.
Okay.
If there is a response, that means there's another client on the same local link that has the same IPv6 address configured. So it will not use that address. It will just abandon that address and will request a new address from DHCP.
And there's no danger in this happening at any other time than just when getting the address initially, or?
Yes, the IPv6 RFC standards, they demand that an operating system that joins the network has to make this duplicate address detection before joining the network. So no matter how we get the IPv6 address, whether we get that through Slack, through DHCP, or through manual configuration, the operating system will always check that there is no address conflict.
So if I put my laptop to sleep and then wake it up again, it will make sure.
It should, when waking up, it should make a duplicate address detection.
Okay. Okay. Good. Thanks.
I can't guarantee that it has been implemented without bugs, but it should.
but it's really low level, or I mean, is it implemented? Where is it implemented?
In the IP stack.
In the IP stack. Okay.
Yeah.
Okay. Thanks.
You're welcome.
So, Carsten,
yes.
I was wondering, you mentioned that the Maestro could, its role could be in the pure static DHCP setup.
Yes.
So, because that's pure and static, what about the use cases? So, before you said that, I noted down, do users need our solutions with IPv6 DHCP? Especially when they have this setup where there are multiple DHCP servers allocating or giving out addresses and marking them as used. So I'm just wondering except for the static DHCP, what is our role as a management layer in this kind of a setup from the user perspective, from the administrator? Where do we help? Because if I see the solution where you have two DHCP servers which are sharing a pool, I mean, is there even an admin of it? It's it's just, it takes care of it.
The role would be here to synchronize the pool configuration, I would say, because you have two different DHCP servers, which might even two different products, might be Kia and Microsoft DHCP. To synchronize the pool configuration, like the start and the end address of the pool, and all the DHCP options, like DNS resolvers, domain name, NTP servers, all that options that come with DHCP.
Yeah, so
synchronize that between the servers.
Yeah. But just for daily running, I mean, would you be in a DHCP V6 setup? Would you be going into the Men&Mice suite and looking at allocated addresses and stuff like that? Because
maybe for troubleshooting.
Yeah. It's just I find it kind of interesting because when looking at your or listening to you, I find it it's kind of a self-managing setup.
Yes.
Which of course it isn't, but it sounds a bit like that.
You have certain administrative actions that you have in Dhp V4 that you don't have in Dhp V6. For example, you don't need to go into a pool to remove old entries because your pool is running full. Your pool will not run full. No.
Yeah. I mean, yeah. About the backup service, because there can be multiple backup services, and you said, for us, we could read the data from a backup service, but could we fake a backup service? Could we talk to the DHCP server and get just the updates because it's asynchronous?
Sure.
Is there a protocol that we could just tap into and get all the data?
Yes, of course. I mean, this is the Kia protocol, and Kia is an open source solution, and it is, I think it's RESTful HTTP.
Yeah.
And the protocol is documented, at least in code, maybe even in writing. Yeah, sure. It shouldn't be too hard.
Might be interesting.
Yeah.
Yeah, okay, thank you.
Carsten, a question relating to what, in relation to this, regarding our role, regarding DHCP options and stuff like that. Are they mainly user-defined options and things like that? Are they void with IPv6 or?
No, the options are what happened with the options is very much the same as with DHPv4. I mean, there are some options that IPv4 only that you can't find in DHPv6, and the other way around, there are some options that only make sense in the IPv6 context. But handling of options is very much the same. You have options that are standard options, and you have user or vendor-defined options. It's a little bit more, the implementation is more clean in DHPv6 because the vendor and user options have been piggybacked on DHPv4 Dhp, but they have been designed into the protocol with DHPv6 from the beginning.
I mean, you have the possibility of accessing NTP server and
yes,
directly. So
yeah, there's of course you could use you don't need in IPv6 you don't need to just use the NTP service addresses by DHP. You could use Multicast for that. But I found that most enterprise companies, they just want to use what they know, and they know DHCP.
Yeah, okay. But what about, as Matti was asking, our role in regards to an overview to the network? You said troubleshooting. Something else that you can think of, for example?
Yeah, synchronizing configurations. Yeah, monitoring, maybe even the systems, whether they are up and running, and the operations, like how many IPv6 addresses are active in the pools. There could be security related stuff, like if there is a spike in allocations on a pool, that might be something to look into, to report to an administrator. I mean, there's probably a lot of stuff that the Men&Mice solution could do here. I'm not prepared to have a full answer for that. Maybe we should meet like with PM and have a session like 1 hour, 2 hours to just do a brainstorming on what we can do with DHPv6.
Absolutely. Can I ask you a bit about the stateless automatic addresses? Is it like, does it make sense to use it? Are like organizations and companies using that?
Yes. The reason being that, and that is crazy politics, Google does not support DHPv6 for political reasons.
Okay.
They only support Slack. That is, every device with the Google operating system, which is currently Android, but later will be Fuchsia as well, does only do Slack. They don't do DHPv6 at all. And Android is not only mobile devices, it's also management software nowadays in industrial applications. And Internet of Things stuff. These things often also run on Android. So if there's any Android operating system or later Fuchsia in the network, you have to use Slack.
Yeah.
On the other side, Microsoft supports Slack only in the latest versions of Windows 10. So when you have older Windows 10, or when you have Windows 8 or even Windows 7 in your network, you have to use DHCP V6 because it doesn't do the full Slack required to join the network. So most companies nowadays end up deploying those.
Yeah, okay.
Which is a pain. Yeah, but you can't either live, at least in a large organization, you can't ignore Microsoft and you can't ignore Google.
I have a small question regarding Dhp V6 addresses allocation. If we are issuing them randomly to a very large pool, would it be impossible to scan for IP
Yes,
addresses and
yeah.
devices?
With modern network speeds and modern computer speeds, it takes roughly 300 years to scan one network.
So you just need like to do a multicast send to a probe to do something similar.
Yeah, you could do that. You can ping to the all nodes multicast address, yes, but that only works in the same link local network.
Yeah.
So you already need to be in that network, then you can do that. But scanning from the outside, that's difficult.
But scanning from the inside would also be very time consuming. So all tools that scan the local networks will be obsolete.
Yes. Yeah.
Okay. Interesting.
Yeah, you have to tap into the switches and routers and get the information from there. The neighborhood caches, the ARP tables.
Yeah, about the when multiple servers like give out addresses and only one is used, so the client checks whether it's like a valid address, but when does it get like invalid on the other servers? Like there are 3 servers, each one gives out an address, but only one of them is used. How long do the others just?
Every IP address given out by a DHCP server has a lease time attached.
Yeah, so it's.
And after that lease time, it becomes invalid. So because after 50% of the lease time, the client will renew with a server from where it received the address. So that server then knows after 50% of the time that actually the client has used that address. And the other server, after waiting 100% of the lease time, then can be sure that this address is not in use anymore and can recycle that address.
Okay. So it's just like a, yeah, it's garbage collected. Okay.
Yes.
Okay. Can I ask you about one thing which is probably not related to us, but
Sure.
as you mentioned, multicast addressing is like, and Germany is like IPv6, is IPv6 country. Do they use like IPv6 multicasting for like streaming or stuff like that? Or
no, I'm not aware of that.
Oh.
Reason being that multicast has a very bad reputation for being complicated and hard to manage. And the reason for that is that multicast was originally designed together with IPv6 in the 1990s and then backported to IPv4. But IPv4 has not been designed to work with multicast. So IPv4 and multicast is complicated and error prone.
Yeah.
IPv6 and multicast is actually a walk in the park. It's very easy and it just works because it has been designed together. However, because multicast has such a bad reputation,
yeah,
nobody really wants to touch it.
Okay, I understand. It's because when I've looked into the current implementations of like multi-streaming, it's just terrible.
Yeah.
There is nothing, everyone is like everything is done n times. So yeah, so I just think it's interesting that in Germany, where it's everywhere, that it is not still used, but perhaps it will one day.
Yeah, maybe we need a new generation of network administrators that have grown up in an IPv6 only world. Yeah, maybe then.
Fascinating stuff. Thank you.
Thank you. Okay, thanks very much for the good questions. And if you have additional questions or need to know something about IPv6 or DHCP, let me know. Just write me an email. And if you like this format of having 1 hour, this time a little bit longer because of the outages last time, but if you like the format, we could do that again in a month's time or so.